Started. Good morning, good afternoon, good evening, everyone, depending on the location. I'm Koji Yamashita, the moderator of today's webinar from UC Riverside. I'm serving as the PS chair of the Algebra Footier section. Welcome to the Algebra Footier section. Our Footier section spans a wide geographical area stretching from West Covina to the eastern edge of California and from Temecula to Baker. Today, we are honored to welcome 4 distinguished power engineers from across Europe. They will introduce an exciting project on multiport converters called iPlug project. Thank you for joining us, Dr. Farag, Dr. Pepecello, Professor Chayamane, and then Professor Beza. Before we begin the presentation, let me briefly introduce our speakers. I will keep it short so we have plenty of time for their fascinating talk. Dr. Ahmed Y. Farag earned his PhD degrees in 2025 from the University of Padua, Italy, where he is currently working as a postdoctoral researcher. Dr. Antonio Pepecello received his PhD degree in 2022 from the University of Sannio, Italy, and is now a postdoctoral researcher at the Catalonia Institute for Energy Research, also known as IREC. The Professor Mark Chayamane obtained his PhD degrees in 2017 from Cardiff University, UK. He is currently an associate professor at Universitat Politècnica de Catalunya, UPC, and co-founder of the spin-off company eRoots Analytics. And Professor Meptu Beza earned his PhD degrees in 2015 from Chalmers University of Technology, Sweden, where he now serves as an associate professor. And with that, dear speakers, the floor is yours. I will stop sharing my screen. Please wait.
Good. So thanks for your presentation. I will start sharing my screen with a general presentation of our project, and then we will go through all our presentations for each work package, which for us it's like the main core of the activity that we have done in the project. So, oh, sorry, no, this is not the good one. Let me see. Yeah, this should be the one. Good. So iPlug project. iPlug project is a project where we analyze a type of polyelectronic device where the idea of this is basically it works like a converter with different ports, different terminals, and the idea is that we can connect different things like storage, distributed generation, also different feeders or different type of loads. And we can connect either AC devices or DC devices, depending on the purpose of our device, of our element. And the idea is that with that, we can kind of optimally locate this element into the distribution grid or into a building to facilitate the massive integration of renewables, also to avoid grid congestion, and also to provide like additional functionalities for the end users and the distribution grid. And here you can see, so its application example for low voltage and for medium voltage. So what we have done in this project is, I mean, we had these objectives I'm showing here on the screen. And basically, first we wanted to understand what were the requirements that we can define for these converters, what type of architecture topologies we can think about as a preliminary study. And finally, which kind of assessment we can do to choose which kind of a converter we need, depending on the elements that we are connecting to it. Then we focus our study in the design of the hardware and control for low voltage and medium voltage applications. And then once we had these elements, the idea was also to do optimal location and sizing of these elements within a distribution grid. Finally, the last technical objective was to evaluate the operation and control of these converters at local level for the device and also at grid level. And also in this kind of projects, we also have to include and other type of objectives more related to the environmental, social, and economic aspects of this type of converters. But for today's presentation, it is something we have removed due to lack of time. This is like a scheme where you can see the members of this project. This is part of what is called Horizon Europe project. It's a kind of typical European project where different universities and companies can collaborate together within the same project. And in this case, we have people from the UK, from Starkey University. We also have from Sweden, Chalmers University. From Serbia, we have the company Typhoon Hill. From Italy, we have University of Padua. And from Spain, we have like 4 entities. CITSE UPC, which is a research center from Technical University of Catalonia. Also IREC, also a research center. And then we have 2 companies, ANEL, which is a DSO, a local DSO from Spain, and also Infraestructuras, which is a kind of a public company that is managing public buildings in Catalonia area. So all of us, we have been organized in these 6 work packages. The 4 first work packages are going to be the basis of today's webinar for the technical content. And then we have these 2 last work packages more for these additional aspects that we analyze for the multiple converters, plus another work package for the project management and coordination. And finally, here you have like our website that you can visit, and also you can follow us on LinkedIn. The good thing is that now we are at the end of the project, so you could see that we have many deliverables that are available for you to have a look. So yeah, based on that, we'll start following this order. So we'll start from work package 1 now, which I will also present. All right, then I don't know how you want to do it. Do you prefer we do all the presentations together, or we do one by one and then some short presentations? What do you prefer to do?
I think all together is fine.
All together is fine. Good. So
yeah,
let's proceed. Yeah, thanks. Great. Then this first work package here, the idea is that we wanted to have this general overview of different topologies and functionalities that we can have from multi-port converters. Of course, that was the first thing we did. So this was a preliminary analysis, but also it was useful to define what to do in the next work packages. And also we did the definition of different use cases. So we had a bunch of use cases, and from those, finally, we chose those ones that were useful for the type of analysis that we wanted to do later on. And you will see in that as part of this work package, there are some of these use cases that has been considered in more detail. And then we also did a methodology. We developed a methodology for sizing and locating the multi-port converters, considering techno-economical analysis and some specific economical and technical indicators. And then we use this methodology also to compare different options, like, for example, what is better, a multi-port converter or just having separated converters with batteries or PV systems located at different points. So that was, for example, one of the comparisons we did. And finally, we did a resilience analysis where we define a methodology to evaluate the resilience. We define a database of hazards and vulnerabilities. And finally, this was used to evaluate for a specific case study how we could improve the resilience of a system with the introduction of an MPC, a multi-port converter. So this is like the overview of the sizing methodology that we follow. Basically, here we had like as inputs, typically like the demand profiles of a system for a full year, the the expected renewable generation that we would have there. Also, in case of having storage systems, the storage parameters, also grid parameters, and cost of all the components that are are considered here. And then, in order to deal with the sizing methodology, considering data for 1 year was a bit challenging. So what we did was to do a selection of representative days, and that could be done a bit arbitrarily or applying some machine learning techniques to kind of classify the days based on some common characteristics. Storage sizing was part of this method, but as a side thing, because adding this storage sizing as part of the methodology, especially in case of considering grid constraints, was a bit challenging. So this is considered as optional part if necessary. And then here we had the main optimization part, where the idea was to mainly minimize the cost of this multiport converter, maximize renewable generation, and then we could consider other type of objectives like, minimizing power losses or voltage variations on the grid. And then we were considering constraints, both technical and economical constraints. And here you have the list of all the ones we did, but just for lack of time, I'm not going through them. And as a result, in case of storage sizing, we could get like the characteristics of our storage system. And for the multiport, the main information is the nominal power of each of the ports, AC or DC ports, and then also some specific KPIs for the technical and economical evaluation of our multiport. And then in terms of applications, we kind of derived like two different options. One that we called energy-based option, where the grid constraints, so all the power flow constraints of the are not considered. And this typically mainly for buildings where the grid side is not that important, or in case of distribution grids where we want to do maybe just an initial analysis without considering these grid constraints. But then the most important contribution is also in this grid-based option, where we actually consider the power flow constraints, and the system becomes a bit more complex to be solved, but also more interesting for the research that we did. And here we have like some examples of applications based on the use cases. So in case of buildings, we use some data from this company that was participating in our project, Infraestructuras. And the idea was to basically compare what was better, either to have like separated devices, each with a single converter, or trying to combine all of them like in a single device like this, or even adding the load as part of these devices. And as an output, we usually get this kind of information. So the power, the nominal, the rated power of the converters of the ports for our multiport converter. And basically here we did also some kind of sensitivity analysis comparing this scenario A with the scenario B based on the costs of the multiport converter or the cost of the different devices separate. And that's just one example for you to see. For low voltage grids, we use another case study, which is shown here. And this case study was coming from the local DSO that was participating in our project. And the idea is that here they have like two low voltage grids, one at 400 volts and another one at 230. And usually in Europe, we have 400 volts, but in this case, there was some kind of legacy grid at 230 volts. And the idea was to instead of like upgrading all this grid, we could interconnect these two systems through a multiport converter. And in this multiport converter also, we could add PV and some EV chargers as an addition. And that was one of the advantages that we see in this kind of converters. And in this case, we consider like different objectives for the optimization, and here they are listed. Basically, the same ones I presented in the general slide. And finally, this was the result. And for medium voltage, we also considered a very interesting case where the idea was to see how our multiport converter can help to reduce voltage difference between different bus bars when the multiport is connected at at the sub-transport level, so at voltages that are very close to the transmission grid. And here you can see, like, this is a very complicated bus bar distribution that we kind of simplified. And in a basis scenario, we see that the voltage variations were not very high, but when considering some kind of extreme load cases where one of the bus bar had more load than another one, then we started to observe some high variations of voltages that we could compensate with a multiport converter. Finally, for the resiliency, here in the project, we also suggested a methodology based on GIS, where the idea is to do a methodology with risk probabilistic assessment, which is a typical method used in other applications. And the way to evaluate the resiliency was based on the amount of power or energy that we lose here. In this case, power energy demand, for example. And here, the idea is to use this software called QGIS. Is an open source software to deal with GIS data, and also along with PyQGIS, this is a package with Python. We could actually program a lot of things from our side in order to include all the information from the power system data, also our resiliency index calculation. And as a result, we've got this methodology that you can see here on the right, where based on a database of hazards, external hazards of the system, and internal vulnerabilities of our system, plus the network information, the idea was to define like different areas and sections for the power system, where we could kind of do a hazard analysis, so combining all the type of hazards depending on the area, geographical area, and this allows us to calculate the probability of hazards for each area. And finally, we could also combine this with the vulnerabilities of our system and the risks, and the impact. And this impact was calculated based on this energy loss for demand, for example. And in that way, we could calculate finally a resiliency index that we could use to compare the options without multiport converter and with multiport converter. And the case study used here was basically another grid from the local DSO, ANEL, and you have here the grid. And this is basically a medium voltage system, where the idea was to also connect in the like a small PV generation system of 100 kilowatts. So for this system, the idea was to identify the hazards, the vulnerabilities, and calculate the system resiliency without and with multiport converter. Here you have the list of hazards and vulnerabilities that we considered. All of this was based on public information that we had from Spain, Catalonia, and Europe, and also from specific information that we've got from the local DSO. And finally, here you have like the evaluation of the resiliency without and with a multiport converter. Here it's a bit small to see. Maybe I can zoom it a bit more. But basically, this was the system without MPC, and we connected the MPC between these two buses. So here you can see, right, that there is a line connecting both of them, but it's actually this multiport that you have here on the right. And these colors indicate the amount of power that has been lost due to the resilience analysis. So you can see the dark colors represent higher power losses, higher power that is lost or energy that is lost. So we can see that when we connect the multiports, actually, indeed, we can see that the amount of power that we lose, it's lower, and this is because the colors are lighter. So that proves that multiport, if we consider a good location for that, in this case, a way to mesh the grid, helps a lot to reduce helps a lot to increase, in this case, the resiliency of our system. So yeah, that's more or less the summary of what we did in this work package. And if you want more details, I invite you to check these deliverables that you have here. And here you have the link from the website where you can do it. Yeah, I think now Matthew is your turn.
Okay. Okay. Can you see my full screen?
Yes.
Yes. Not full screen, but yeah. So I can see the present and the PowerPoint file. So if you go to like a presentation mode, that will be better.
Okay. Now?
I think it is coming.
Is it coming or?
Mm, I think it's visible. So yeah, just you know.
Maybe I will try to share
Okay.
a different share Windows. Now?
You
No
have to go into
change.
slideshow mode. Slideshow is one of the menu items, top of the window. Slideshow.
Yeah, I press that
SLIDE.
button. Yeah, I press that button or F5. It should come. It shows me full screen for me. Okay, I will try one last time. Another option. Entire screen. Yeah. Is it
Yeah,
working?
now,
Or?
yeah, it is working. It is
It is
working.
working.
Okay. Okay,
Clicking on
good.
the next to the stop sharing button is a hide button that will hide the
Yeah,
banner
I
which
will press
obscures.
that. Okay, it means
Perfect.
you are looking everything. Good. Okay, I will present one of the work packages of the project, and it will be specific on the circuital structures of a medium voltage multiport converter. Mark already motivated the need for multiport and its application for low voltage and medium voltage, looking the multiport as a black box where you have different ports to realize. But I will go deeper into the circuitry structures where how we can realize a medium voltage multiport. So having known the motivation why power electron converters in distribution grids and why multiport, that's because by having an integrated solution, we could have a reliable, efficient, and modular and high density converter solution than using separate converters. So that being the topic of discussion, what are the options and what do we come up with being the best alternative, the best option to implement this multiport would be the discussion point. So for that, we have a case study to aim for the design. So we aim for example, for a 3-port multiport converter where we will have, I will use a pointer. We will have 2 AC ports, medium voltage, and a low voltage DC port where we used to integrate energy storage. It could be, or could be EV charging infrastructure, or it could be PV integration. So having a solution, a multi-port converter solution to integrate 2 medium voltage AC ports and a low voltage DC port. And of course, from a black box point of view, that this is something that Mark considered to use it in the system and evaluate. Inside the converter, we have to see, okay, what are the options, what are the difficulties, and the advantages would provide us with different solutions, because there could be multiple solutions that would fulfill interconnection of medium voltage and low voltage grid. And the discussion being multi-port and medium voltage, which means that we have to start with the use of multi-level converter topology, where we have to use serious connection of small modules to realize the medium voltage. So that is a prerequisite that we will use. And when we talk about multi-level converter, it could be half bridge cells or full bridge cells. Which option to go for? What the advantage, disadvantage in each, we will see. And that's the things we will do. So part of the project would be to make a literature review of how we can have a circuit structure to realize a medium voltage multiport for this configuration. And we will evaluate the flexibility to increase the number of ports, to adapt it for different voltage and power levels. So the first main task was to select at least 3 candidates which could realize this configuration. And we started with a very mature technology where for medium voltage interconnection of 2 AC voltages, we could use a back-to-back connection where we will have a medium voltage DC port and from which we can realize a DC-DC stage to realize the DC port, which is low voltage. Another option is to integrate all the ports using high frequency transformers or using DC-DC converters, where there will be an isolation between all the ports. The advantage with this is that we don't need to realize a DC voltage level here, where the number of components could be better, but there is operational difficulty with topology. And the last one is to use a back-to-back configuration similar to this one, but using full bridge cells instead of half bridge cells. By using full bridge cells, it will provide a number of advantages. One of the main ones being the DC voltage, common DC voltage we create is independent to the AC voltage, which means we can reduce that voltage to reduce the number of components and realize the DC port quite easily. So what I will do would be in the coming slides, highlight the advantage, disadvantage of each topology, and which of these would be a pick to use for our multiport medium voltage application, which we will go on and try to do a lot of simulations and provide a prototype in the laboratory setup as well. So if I start with the first one, this is a detail of one port. This is the AC side. We have a medium voltage, intermediate, medium voltage, common DC voltage, where these are half bridge cells. So this is a very common and mature technology, which is a multi-level converter in WI configuration, we call it, where we realize a medium voltage DC voltage. The disadvantage with this is that the DC voltage level we have here and the AC voltage are coupled somehow. So both would be also in medium voltage range, and which means that if we have to realize two AC voltage of different levels, then it will be difficult. We have to either use transformers or we have to change the configuration. So modularity will be somehow lost. A medium voltage DC means also that difficulty handling DC faults. And yeah, those are the disadvantages. On top of that, we have to realize a low voltage DC port, which means that going from medium voltage to low voltage DC will need its own modular solution, which will increase the number of components. So as a start and as a mature technology in a back-to-back setup, in soft open point configuration, for example, but for the application where we have to integrate two AC voltage levels of different magnitudes and realizing a low voltage DC, this is a bit difficult. So then the next topology we see would be something that mitigates this one. And the first thing we thought was to then integrate all the ports using AC without a common DC voltage. That means a configuration like this. We have AC-AC conversion where the common AC in all of them is coupled using a DC-DC stage, high frequency DC-DC stage, or high frequency transformer, we can call it. So which means then we can realize the different AC voltage levels by using different voltage transformation ratios in the active bridges. The low voltage DC can be easily realized by using an active bridge dedicated for realizing the DC port. And that's the advantage. So it somehow mitigates the difficulty of the previous topology. But the main challenge with this topology is that because all the ports are coupled somehow without a decoupling common DC voltage, so operation during unbalanced or faulty conditions is a bit difficult. And that's a challenge we have to deal with. So continuing with this evolution, then the next thing we see would be then to use a back-to-back setup like in the first one, but instead of half bridge cells, we use full bridge cells. And of course, this will increase the number of components because full bridge cells use twice the components of a half bridge cell. But the advantage is that as such, we can decouple the voltage level in the AC and the DC voltage, which means for an operation where we can reach the DC voltage to a lower value, realizing the DC voltage using an isolated stage would be easier, and dealing with DC faults would be also much easier than the case where we use half bridge cells. So this is one of the candidate topology we can use, and it fulfills all the requirements we want, such as it can integrate different AC voltage levels. Having a common DC stage means that we somehow create a decoupling between the ports where operation in unbalanced and DC AC fault conditions is much better than the previous condition. So as a summary, from the three configurations we have seen, these two are the topologies that we can compare. This one is typical characteristic is low number of components. A typical characteristic of this one is good operational conditions. So we optimize this hybrid solution where we have an isolated DC-DC stage to realize the low voltage DC. but by choosing a DC voltage level lower than what we would have had if we were using half-bridge cells, it's possible to compensate for the number of components we have in here and we have in here. So if we design this converter where we can make the number of components somehow similar, the only thing to differentiate between the topologies is operational complexity and how flexible they are for different operations. And we compare qualitatively which one will be better, so that to recommend which topology to use for our application. So we have some kind of qualitative comparison. And we did that for the comparisons in terms of handling AC faults, complexity. This is to mean how the design can be adapted for different voltage and power levels, and how to deal with unbalanced operation and different fault levels. We have found that this topology outperforms in a qualitative analysis than the fully isolated topology, and the reason that we recommend this is the topology to go for. Using full bridge cells in a back-to-back setup and choosing the voltage level which is a little bit lower than what we would have had in the full bridge, lower than half the value we would use in a half bridge setup, and using dual active bridges and isolated stage to go from intermediate DC to low voltage DC. And to realize this one, we use a series connection of input side and a parallel connection in the output side. And this is the topology we go for. And for that reason, we do a lot of simulation tests and laboratory experimental verification of how, as overall in normal and abnormal conditions, this converter topology works to verify that the solution is feasible. So that's what we did. We did a number of tests in both simulation and laboratory setup. And in the coming slides, what I will do would be a selection of some tests that this topology works in the laboratory. And of course, it says as application is in medium voltage, and the tests we made in the laboratory is low voltage somehow, but fulfilling that we are going to realize different voltage levels on the two AC ports and a DC port, which we connect a DC load. So to realize that one, we have a number of resources in Chalmers. And if I present that one of the ports we use multi-level converter, where we have an empiric system with 4 sum modules per arm, per phase 8 sum modules, full bridge cells, and which is a DC voltage level, which is optimal as the design. And in the other side of the AC port, we use 2-level voltage source. So the DC side of these two converters are coupled to make a back-to-back. And by having a DC voltage level and a multi-level converter, we're using full bridges, we can somehow decouple the voltage we realize in this port or in this port. On the DC side, we connect a resistive LED to realize DC load. And because this is low voltage, we did not use an isolation stage, but in medium voltage application, that has to be implemented. And having this, we implemented a number of tests where we apply load steps in the DC port, for example. We apply some kind of faults on one of the ports. The 2-level side is connected to also an array load where we have the converter operated in grid forming mode. And this has a classical vector current control and outer power controllers and DC voltage and energy controllers. We have tested a number of the conditions to see that this in fact works as we intend. So the first test is to apply a load step at the DC side. What we did was to choose a resistive value of the load, which automatically would mean that there will be a different load step because the DC voltage level here is controlled from AC port 2 side. And we see that when we apply the step, and of course there's a different output from the converter, the DC voltage level is controlled. And we could see that the sub-module capacitors are balanced within range, which shows that the operation is possible. But we could see that there's a low oscillation in here in the power step on AC port 2. And of course, that's natural due to the high capacitance we use in a multi-level configuration for the multi-level converter. And of course, we have to test also a number of unbalanced operation or abnormal tests like faults and unbalanced operations. With a conventional operation, if we apply one phase fault, a little bit of a dip, we could see that there will be unbalanced current exchange, which affects the active and reactive power exchange, and the circulating currents or the currents in the arms of the modular multi-level converter will be a bit unbalanced. By applying, of course, ways to mitigate the negative sequence components in here or the imbalances in the arm currents, it's possible to have a full balanced exchange on the AC side or the DC side. Which means that if we see with the conventional control without those mitigations, we could see that the capacitor voltage would go away from each other, which is a basic need for a multi-level converter to operate normally. By applying balancing controllers on the energy of the sum modules and the arm voltages, it's possible that the capacitor voltage can be kept within range, and then we will have an operation which is good. So all of these details can be found in the deliverable, and that can be referred, but these are some of the peaks of the results we have in the multi-port converter, which is realized using full bridges in a back-to-back setup and an isolated stage to realize the low voltage DC stage, and yeah, showing that the operation is feasible. Thank you for listening, and that was from me.
Mepto, could you stop sharing?
Yeah.
So I hope now you see my full screen, right?
Yes, I can see your screen.
Okay, thank you for confirmation. So my name is Hamad Yahya, and I'm going to present the activities of work package 3, which mainly focuses on the low voltage multiport converters. So for the low voltage scenario, we split our work into 2 levels. The first level is the distribution level, so similar to the medium voltage case. We consider the distribution grid. So with the multiport converter, we could integrate multiple feeders with renewable energy sources or energy storage or EV charging stations. Or the scenario that is specific for the low voltage is the residential level, basically to align with the European Union vision for future buildings to be zero net energy buildings. So in this scenario, you will need to have your energy sources, your energy storage, and the interconnection with the existing grid. And we believe the multi-port converter can be more efficient in this scenario compared to using multiple converters. So again, a quick recap. So our main motivation is to replace these multi-converter scenarios with a single multi-port converters. So with this, we aim to minimize the number of conversion stages. And with this, we potentially enhance the efficiency. We reduce also the number of components, and we reduce the total size and cost. And we have some additional flexibility because with the multi-port converter, you enable direct power sharing among different ports. Unlike the multi-converter scenarios, you will have some power circulation from one port to another. So for our low voltage scenario, the first challenge we have faced is the standardization of the DC voltage level. We still don't have a specific standard for voltage levels. For DC voltage levels, you can see the levels spanning from 12 volt to 1.5 kilovolt for low voltage. And this not only affecting the selection of passive and semiconductor devices, but also affect the selection of the topology itself. If we are talking about the European grid, if you're going to interface a system higher than 566, you need a boost type rectifier, like the voltage source converter. If you are going to interface less than 490, you need a buck type. So this was our first challenge. Of course, we had a lot of studies that pushes towards the 400 DC volt to have overall improved efficiency and cost, but we have strong motivations to have a buck boost topologies to be able to cover as much as possible from these levels. The second challenge with the existing structure of multi-port converters. So maybe the easiest way to build a multi-port converters is to use the DC link coupling approach. So you couple conventional AC and AC to DC and DC to DC converters to a bulk intermediate DC link. With this, you build the multiport converter, but of course, you still have multi-stage bulk conversion, so efficiency is affected, and also you need a bulky intermediate capacitor. The second approach is to use the magnetically coupled multiport converters, so you need multi-terminal transformer or coupled inductors. Of course, you gain advantages like isolation and potentially 0-volt switching, but you need an bulky component, and also it's very complex to design this multi-terminal high-frequency transformer, and potentially the efficiency and power density is compromised. Finally, there is some solutions that re-adopt multi-level inverters into multiport converters, but these solutions usually have some limitations on the power flow, so they don't have the bidirectional power flow capability at all ports, and also have some dependence between the power flow and the voltage ratio. So that's why we proposed some novel topologies. The solutions we have proposed, all starting from this basic topology, is called the Y converter. It has some interesting features, like it has a buck boost capability, has bidirectional power flow. So we extended this topology first, so what we call the multiport Y converter. So instead having 4 switch buck boost for each module, we extended to have 6 switch buck boost. So we interface the 3-phase AC grid with 2 DC ports. We still have single stage bulk conversion. We don't have any bulk components like intermediate DC link capacitors or high frequency transformers. We have bidirectional power flow, buck boost capability at all ports without any dependence on the voltage. So we have enhances flexibility. And also we proposed another solution we call the asymmetric multiport. So instead of having 6 switch and 3 inductors for each extra port, we use only 1/2 bridge leg and single inductor, and this is suitable more when interfacing a lower power port. So we start first by answering the fundamental question. So does this multiport converter attains at the end an improved efficiency and power density compared to the multi-converter solution? So this was our first study we have conducted. So we analyzed the efficiency or the power losses of both solutions at the whole operating range of B1 and B2. And what you can see here is the larger blue area means lower losses. So with the multiport converter, we have for the most of the operating range lower losses compared to the two converter scenario. And this is mainly driven by the direct power flow, so between the D systems. So in our case, you can exchange the power directly between the DC ports, but when using 2 separate converters, you need to go from DC to AC and then go back from AC to DC. And of course, we have also reduced the number of semiconductor devices from 24 to 18. We moved then to a more detailed evaluation. We considered a specific mission profile. So we have the connection with the grid. We have our PV generation and energy storage, and this our profile. And then we did a Pareto-based evaluation. So we have a very wide range of solution. We have a large design area, millions of solutions, and we compare only the Pareto optimized solutions for the multiport converter and also for the 2 converter scenario. And as you can see, both in terms of efficiency and power density, the multiport has shown an improved performance. Also some highlights for experimental validation. We used an approach is like a rapid prototyping approach. So we used also some half-bridge modules from Imperex, and we also realized our modules to realize the AC side half bridges to have low capacitance and also higher current devices. And we have tested this in different scenarios, including steady state and transient. Here we do a step change in one of the board where the other is fixed to demonstrate the full decoupling between boards. And also in this scenario, when we do a step change from rectification to inversion, so in this case, the grid we're supplying the two DC boards, but when one of the boards, instead of consuming power, it injects power to the other board. And as you can see now, almost no contribution from the AC grid, and now the DC boards are exchanging the power between themselves. We did also an efficiency evaluation, and of course now as we are considering a 3-port converter, the efficiency moved to a 3D plot. We use this contour plot for better demonstration. We have our x-axis B1, y-axis B2, and then we have the color to present the efficiency. And even we are using this rapid prototyping, which is not optimized for efficiency or power density, we attained a big efficiency of 96%. So yes, finally, this a quick recap. So the main challenge in our new systems are the rapid penetration of these systems, and we aim to optimize the coupling between existing AC and the upcoming DC systems. We believe that the multiport converter is a good solution. It enhances the efficiency compared to the multiple converters, and these are two of the solutions we have presented in work bucket 3 of the iPlug project. Of course, we have a lot of other studies like the fault right through nonlinear control of these multiport converters, and also impedance specificity of multiport converters. All of this you can find on our repository on Zenodo for iPlug. Also, this my email and LinkedIn if you would like to discuss further any of these activities. And thank you for your attention.
Okay, thanks a lot, Yahya. I will share the screen for the last presentation. Okay, so I'll proceed with the discussion on the applications of multiple converters in distribution grids, in particular regarding their optimal operation and the stability analysis. So, well, based on the background that we have from previous presentation, we know that the grids are facing a lot of changes in the last years, and we need more flexible assets in order to avoid problems such as thermal overloading of power lines, larger voltage deviations, bidirectional power flows, or increased congestions. In order to face these challenges, we need new technologies. The on-load tap changers or the traditional switches that were designed for the traditional grids are not anymore sufficient for the reliable operation of grids, and soft open points are one of the technologies that can enable this greater flexibility of the grids of the future. Our idea in the iPlug project is to employ multiport converters as parts of the soft open points, such that we can enhance the current soft open points that are based on just 2 ports. So they are devices that consist in 2 back-to-back voltage source converters that they connect different feeders within a distribution network. And by using multiport converters, we can enhance them and add more ports to them. For example, in this case, you can see a 3-port soft open point with the connection to 2 feeders, so a distribution grid and distributed energy resources. So I'll focus mainly on this application on multiport converters. These are some of the applications of soft open points that are available in the literature. Until now, we have mostly focused our attention in loss minimization and voltage regulation for the multiport soft open point. In order to assess what would be the benefit of using a soft open point, we solved an optimal power flow problem whose objective functions were voltage regulation and loss minimization with some changes. So in order to take into account the soft open point. So of course we would have the power flow equations, the node power balances, and what we add are the balances at the different ports of the multiport soft open point. In this case, we could have a connection to other nodes, and that would lead to an additional node power balances, or we can have one of the ports connected to distributed energy resources. In this case, if we have a flexible DAREs, for example, my battery and a PV plant, then the inequality would hold. Otherwise, if it's non-flexible, we would have here an equality constraint. Then we have the total active power balance in the multiport soft open point, and finally the technical constraints. Of course, this initial formulation can be enhanced with the integration of battery models or fuel cells or any other distributed energy resource that is connected to the soft open point. So moving to the case study, the initial case study was based on the well-known IEEE 33 bus system. As a benchmark case, we didn't consider the multiport converters in the system, and the limit, we considered the limit of plus minus 3% of the nominal voltage and a large load scenario in this case. So in figure 1, you can see that without any enhancement of this distribution grid, we have some under voltage problems starting from some of the nodes, considering the radial nature of the topology and lack of distributed energy resources or other reconfiguration devices. Let's move on now to the case study in which we consider the soft open point. In this case, we have a 3-port soft open point. It's connected to 2 buses, bus 33 and 18, and the third port is connected to distributed energy resources. In this case, flexible ones. From the figure on the right, you can see how by optimizing the active and reactive power flows provided by these ports connected to the feeders of this soft open point, we can significantly improve the voltage deviations in all the buses of this IEEE 33 bus system. So in the purple curve is the one with the optimized soft open point, whereas the other one was the benchmark case. We investigated what's the impact of having a soft open point in different locations of this particular system and in general in radial grids. And what we have seen is that it's very important to choose the correct location of the soft open point in order to maximize the benefit once we optimize its operation. For example, in this case, if we consider the gray curve, so multiport converter between bus 22 and 25, the improvement with respect to the base case is low. Unlike, for example, the current location between 18 and 33. We did a similar case study. In this case, there were some distributed energy resources and overvoltage problems. And similarly, in some cases, if we optimize the soft open point and we locate it correctly, considering also the operation, we can see how it gets back to normal within the limits. Similarly, the soft open point was evaluated in the loss minimization mode. In figure 5, you can see the different positions of the multiport converter. And if we take, for example, the best position up to now, that is between 18 and 33, we can see how the losses, the optimized losses thanks to the optimized operation of the soft open point, are reduced to 1/3 of the original losses in the benchmark system. In this figure, we can see also something interesting, that is in position 1822, for example. If we optimize the soft open point, multiple soft open point in such a way that the voltages are minimized, then we increase the losses more than the benchmark case. So we have adversarial effects that may be unexpected when optimizing the operation of the soft open point, and in case a grid operator would work with these devices, it should be careful of these potential effects that may improve one aspect but degrade the performance in another. We extended the analysis to more than one multiport soft open point, and at least for radial grids, we noticed that the addition of more soft open point, apart from in addition to the first one, does not significantly increase the benefits. So the first multiport soft open point can increase a lot the benefit of the grids in terms of the voltages, losses, or other parameters. Whereas when we start to adding more than one, the benefits start to be more incremental. From the benchmark case study, we move to a real case study. This is a grid from our partner DSO, ANE, and the case study, similar to the one that was presented before by Mark, was based on a 3-port multiport converter that is connected to two low voltage grid, one and 400 volt and another one to 230 volt, with the third port connected to a 100k kilowatt power plant. So first we have visualized the grid as a graph in order to understand which were the features of these two grids and where the soft open point would be connected and how it would affect the different parameters. Then we modeled it in Simulink. Here you can see the two grids connected by the soft open point. And the first thing we did before starting the analysis was to check that the model of the multiport converter and the controls worked correctly. And indeed here, although, well, this is doomed, but actually the transients are quite low and the control can actually follow the reference. In this slide, figure 11, you can see how by controlling the power flows in the different ports of the soft open point, we can have a large effect on the voltage deviations in both grids. Of course, if we consider that this is the position of the soft open point in the two grids, you can see how the effect is greater closer to the soft open point and it goes decreasing. But in any case, it's significant. In addition to the centralized optimization, so once we have set the active and reactive power set points for the soft open point, we've also studied how the local control works, so how to control the soft open point locally. And in this case, what you can see is the model that was developed by my colleagues in AREC, in which we have a triple active bridge in the middle and the inverters that are connected to the feeders. So one of the ports are connected directly to the distributed energy resources, and then the other two to inverters. We also carried out a small signal stability analysis of the system. So after developing the generalized average model, also the linearized version was developed, and the small signal stability analysis was carried out. Here, for example, you can see how the grid parameters affect the small signal stability of the system. So indeed, the XL ratio has a big impact on the stability of the system. Something that is very interesting of these multiport converters is that, especially actually this soft open point, is that they can have different combinations of the power flows, not only outgoing power flows or input power flows, but combinations of them, since there are 3 ports in total. And the different combinations of the flows lead to different considerations regarding stability. We did the same also for control parameters and other grid parameters. And finally, we are carrying out some power hardware in the loop and control hardware in the loop testing. For the power hardware in the loop, the main idea is to validate the centralized optimal control of the soft open points. And in this case, one soft open point is modeled, well, actually, the grid is modeled, and one soft open point is simulated with grid emulators connected to load cabinets. And we have an optimizer that provides the optimal set points to the ports of the soft open point. And we have also been carrying out the control hardware in the loop tests in order to evaluate the primary control. So in this case, we're using Opal and grid emulators, and in the control hardware in the loop, we are using Typhoon and the rapid prototyping for control in order to rapidly set up the control board with the control that has been designed for the soft open point. And that's all from my side. Thank you for your attention. And I think now we are ready for any questions or curiosity if you have any from any of the presentation.
Thank you for the presentation. Unfortunately, the time is almost up, but so if you have any questions, please use the chat window and then type your questions. But before that, so I have not expected that 2 ports are for 2 different feeders at a different voltage levels. I just assumed that 2 ports are for like batteries and then like a PVs, something like that. But so my question is, when a fault happens at one of the feeders, and then can this MPC keep connected, or it is disconnected? What is the operation when the fault happens?
Okay, yeah, that's an interesting question. I will start then. Yeah, if my colleagues have some additional comments, they can add. Yeah, in this case, for example, in the case that I've shown, there is a triple active bridge, so there is isolation with the frequency transformer. Anyway, yes, in any case, the fault operation would be problematic for now, at least in the from the grid point of view. We haven't analyzed in depth what happened in case of a fault when you have different voltage levels. It can be quite unsafe, I would say. So yeah, it's definitely something to consider. But I think my colleagues, maybe from UPC, I think they developed a fault right through control. I think some of the studies have been done by my colleagues in the other farmers. So
yeah, exactly. Thanks, Antonio, for mentioning it. Actually, this question is very important. What we want to ensure is that this multiport converter can handle any fault, and most importantly, any fault in one feeder does not affect the other feeder. And we are been testing in so far with grid following converters, and our objective is also to test it even with grid forming, in case that happens. So yeah, it's an important thing that we believe it's a key thing to analyze to make sure that multiports can be integrated into the distribution grid.
Yeah, thank you. Yeah, because my concern is if we have different voltage levels, then the fault write-through requirement can different depending on the connected voltage levels, right? And then if we have 2 ports at a different voltage levels, which requirement we should follow. So that is so because there is no like standard at this stage. So I think after this project is over, you can also propose some kind of new standard for the multi-port converters. Yeah, that is my expectation. And also, can you check the chat window? We have one question from audience.
Yes, I think Daniel Peters raised his hand.
Yes, I do have a question. Am I audible? Can you hear me?
Yeah. Yes.
Hello?
Yes.
Okay, so the question I have is, when you were designing your simulated networks, were you constraining the design of the converters to commercially available designs, or is it just a nominal design that could be of any values on performance?
Okay, so from the when at least in my case we do grid analysis, we don't consider like a very detailed model of the converters. It's true that these very detailed models have been studied, for example, in work package 2 and 3 by Yahya and Meb2, but yeah, for grid studies until now, no. If I got the question well, yeah, we don't consider in that like yeah.
So just to
In a
summarize,
very detailed one, yeah.
these would all be custom built converters, multi-port converters, because they're not really available for purchase off the shelf. Is that a fair understanding?
Yeah, they're
Yeah, I
not
see shape.
available at this moment. Yeah.
Yeah, no.
Yeah, that makes sense. Okay, thank you.
Yeah, just to add that, yeah, I think Yahya and Meb2 have made some prototypes of these converters for low voltage and medium voltage.
So Antonio, can you see the chat window? We have like a question regarding the maintenance frequency and something else.
Yeah, regarding the maintenance, it's a nice question. I haven't thought about it. I don't know if my colleagues have some ideas regarding the type of maintenance and the frequency of maintenance.
Well, I would expect that if the topology is based on these soft open point options, maintenance will be very similar to standard inverter. But if we go for these isolated topologies, I'm not sure. Maybe my colleague Yahya or Meb2 can add a bit more, but these topologies are a bit more newer in this sense. So maybe the maintenance that they require is a bit different.
Thank you. And then also another question is regarding the grounding system. So can we use like a ungrounded system?
Well, yeah, I think that's also an interesting question. I think we haven't had a look to this kind of configurations, but maybe just as an initial guess, I would say that yeah, it should be possible to do that. Yeah, but well, if my colleagues have other more specific answers, yeah, I will let them.
Yeah, I could add here, but I am not sure what you are referring to, Liz. But if it is from the AC side, I mean, all you need is interconnection point, so it should be independent of that. It should work. But maybe you can elaborate exactly what is different in the delta or ungrounded or a normal setup. You mean, and we can say, but we haven't. There is no restriction where you can integrate different ports.
Okay, thank you. Because the time is up, so yeah, I will share all of the the questions on the chat window later on. I will email all of the speakers later on. So anyway, everyone, the next webinar will be held on August the 13th at around 3 p.m. So that time we will invite a professor from China to cover cybersecurity topics like false data injection attacks against power systems. And then flyer will be uploaded to the Archway Footage section website in a day or two. So please stay tuned and enjoy the rest of the day. And then again, thank you for the wonderful presentation.
Thank you very much. Koji, good job. Hi, I'm Max Cherubin. I'm the chair of the Foothill section. And Anthony, I just want to let you know, thank you for the presentation. Did I say your name right?
Antonio.
Antonio, I'm sorry.
Antonio.
Okay, I'm kind of drowned. It's kind of missing. Your name's kind of missing with my CC, you know, the closed caption.
Yeah.
But anyways, I just want to thank you for the presentation, and we're going to send you a $25 gift card. And thank you. Okay, that's all. Yeah.
Well, thank
And
you.
Koji,
Thanks
thank
for
you,
inviting
Koji.
us. Yeah.
Thank you all.
Thank you
And thank you for everybody attending. Yeah.
Yeah,
Have
have a
nice
great
day.
night.
Yeah.
Bye.
Thanks.
Yes.
Yeah.
Bye bye.
Thank you.
Yeah, bye for now.
Thank you.